Hi, everybody. Hey. Hi. Welcome to the second session of the morning. My name is Leigh Ann DeLyser. I work for CSNYC. I'm the Director of Education and Research. And in my tenure here in New York City, I've also worked a lot with teachers in and out of classrooms. And in my background, I was a high school teacher for 10 years before going to Carnegie Mellon, first as a faculty member and then as a grad student, to study computer science and psychology, so how students learn. And throughout my career, I've always been an advocate for computer science for every child, regardless of their background. And as you can imagine, that left me with some very differentiated classrooms, right? I had high percentages for the school district that I was in. It was outside of New York City, of special ed kids, especially in my introductory to CS classes, because they could earn a fourth math credit for graduation without taking pre-calculus or without taking the Math 3 that was available through the school district. And so coming up with strategies to deal with students who are on track to finish the advanced placement exam by the end of 10th grade and seniors who took 2 to 3 years to pass Algebra 1 in the same classroom at the same time made for an interesting challenge. And so this talk is directly out of the work that I did first as a teacher, and then as I went and became a PhD student and started studying cognitive psychology and all the things around the development of expertise and how students learn, it really helped shape a lot of the coaching I did at the Academy for Software Engineering, and I'll show you some examples that the teachers had done there. And then now the work I'm doing to help inform professional development providers here in New York and the stuff going on. So a little bit about me. I'd like to know a little bit about you guys. How many people in the room are classroom teachers? Oh, fantastic. I love that you're distributed around because we're going to do some work at tables where your experience is going to help. How many people, either as a classroom teacher or as a part of a program, write assignments that students will complete? Great. How many of you struggle with figuring out a way to make those assignments work for 30 kids at the same time or more? Yeah, absolutely. All right, so like all good teachers, I've prepared a small warm-up. And what I'd like you to do is, with your tables, take a minute and give your name. This is our warm-up here. And then instead of writing down, we're going to say this out loud. I would like you to give your name and give 3 words, max 5 if you really need it, that describe differentiation. We don't want to necessarily provide a definition. Is there anybody in the room who've not heard the term differentiation before? Okay, I wanted to make sure. So I don't think we need to describe it clearly for each other, but what does it mean to you? If I were to do this activity, I would say, my name is Leigh Ann, and differentiation means different kids, different outcomes. Yeah?
My name is Joe Vendetto, and to me differentiation means importance, labor-intensive, and sometimes practical.
Great. Joe, that's the exact example of what I'd like everybody to do, but with the people at your table. Because if we were to go around the whole room, we'd be here all morning, and nobody would get to eat lunch. All right, so I'm going to give you 5 minutes. Your name, if you'd like to give where you're from or what school you work with, that would be great. And really quick, what does differentiation mean to you in the classroom? One of my favorite things about that is watching people nod at each other as they say things. How many people wanted to say the same thing someone else said? How many people heard a new word that they wouldn't have necessarily thought of in their first time around? Good. I love it. So I like my students to be reflective, and not only reflective about what I am asking them to learn, but what I'm asking them to say. And so for the educators in the room, what word is missing from that slide? When we talk about differentiation, there's generally a second word that goes with it. Students. Assessment. Outcomes. Oh. So I was thinking instruction, right? The phrase that we constantly hear is differentiated instruction. That somehow we have to tailor the concepts that we're introducing to students to meet them at their own individual instructional needs. right? And something that makes computer science a little different, at least for the short term, is that the work we're doing, we have this assumption that many kids come to us without an extraordinary background in the subject. Many of the concepts we're introducing, even if they have some background, the concept themselves or the depth at which we want the understanding to pervade is new. And so you can't necessarily differentiate that instruction because everybody's kind of starting in the same place, right? And even if they weren't, best practices in New York City, how long should you actually talk to the kids like this as a lecture in your classroom? What's the general accepted practice in your building? How long do you actually lecture in front of your students? 10 minutes. How much?
Student's age.
The student's age, right?
Yeah.
Similar to the amount of time you make them sit in timeout, right? If you think about that for a minute, it really is.
Yeah, absolutely.
Yeah. Anytime that they're waiting on, I tell this to the teachers I work with, anytime they're waiting on you, like waiting for instruction to be delivered on high with bated breath, you only have them for a really short amount of time. Because I don't know about you, but my kids don't wait with bated breath for instruction to be delivered on high. So when we think about it, we really want to move away from this idea of differentiation as multiple starting points for the kids, right? Some kids start here at the beginning, some kids may have a little bit of knowledge, they jump in from the middle, and some kids might be in a completely separate realm, right? And when we think about assessment, we think about it the same way too, right? Would all of these kids do the same assessment? There's lots of writings and recommendations out there about how to make worksheet A and B and maybe let the kids pick between the two different assignments, right? Old-fashioned differentiation was do problems 1 through 15, and for extra credit, do 15 through 20. Do you remember those days? Either having been a student or a teacher way back when? And so standard differentiation is all about different kids doing different activities. And honestly, what do these two groups of kids think about each other? If somebody gets a white paper and some group of kids get white papers and some group of kids get pink papers, what do the kids do that we hate?
They think there's the smart kids and those are the...
Yeah, oh, I'm in the smart group. I got the smart paper, and they're the stupid kids. They're always getting the stupid papers, right? Even if you remix them over time, they still look around the room to figure out who's at the smart table, right, and who's at the slow table. And those expectations they set for themselves, regardless of whether you've created that expectation for them or not, right? And then also, for this kid here who starts at the beginning, who often needs that extra support and scaffold, odds are, but I'm a high school teacher, by the time he reaches me in high school, school has been largely about failure for him. His inability to get to the pink box, or to get all the way through the white box. He's constantly had feedback that says, no, it's not good enough yet. And how many of you have heard them say, I don't know where to start? Right? Especially in computer science. It can be so daunting when we ask them to make something for us. They don't know where to start. And so in differentiation and the way that I'm going to present it to you today, it shifts this paradigm a little, and it wants you to think about everybody starting at the same point and exiting in different places. There is no assignment for the smart kids and assignment for the slow kids. They're all doing the same assignment. And they exit the assignment at different points based on the time limits you place on it and the work that they put into it. And that's really important to stress to them, is it's not about how smart they are when they exit, but instead the amount of work that they put in takes them so far within the time period allotted. That sounds a lot like Carol Dweck's theories of intelligence, right? Fixed versus malleable mindset, except we're not just telling the kids you can do whatever you want. The amount of work and amount of time you put in dictates what your grade will be for all of them. And then they're all working on the same assignment. These different colors are simply shades of the first assignment that engage higher order thinking and more abstract reasoning to give those kids a challenge. And the best part of it is the further you move up in higher order thinking, the harder it gets for the kids to do. And so this kid, who probably could have like passed your final exam a week ago, he's still not done because of the open-ended nature of the end of it, right? Super easy for them to get to the first line. Exponentially harder for them to get a perfect score. And so keep that thought in your mind, is that the way for this is not that there's just more work in each of those levels, but it's deeper levels of thought and requires the kids to be more open-ended in their reasoning in order to get out that top end and get the highest grade. So what defines the exit points? I read this paper, for those of you who are like research like me, I don't even remember how long ago. I think it was like 2002. I was a high school teacher. I was struggling with all these different kids in my classroom. I didn't like giving extra credit because the only kids who did the extra credit were the ones who thought they should. And they were not the ones who needed it. And I didn't want to make like assignment A and assignment B, and you do assignment A and you do assignment B. I wanted to look for ways to take the same assignment for every kid and think about being able to grade them based upon the work that they put into it. And Raymond Lister and John Leaney wrote this paper, they're from Sydney, about giving final exams in a college level course, where they consciously chose the questions on the final exam to align with different levels of blue. And in order to get a C in the course, you could answer all of the questions that were simple knowledge comprehension questions. Here's the information that I have learned, even if I just went and studied the textbook, I could regurgitate it to you. You could earn a B in the course if you then took that and applied it in some new situations, right? And then there was always the one big killer problem that took them from a B to an A, that really distinguished kids and really had them do some creative and higher order thinking. And by structuring their exams that way, they found they had fewer dropouts. They didn't have to curve their course scores as much, because college professors, and Mark is sitting there shaking his head, he's a college professor at Carnegie Mellon, we like to challenge our students, right? We like to make them think. And so sometimes we write exams that are all that big, challenging, crazy question. And so this really also helped them think about a way to get their kids to demonstrate what they have learned, in addition to what they'd like them to aspire to be. I'm going to share these slides on the bit.ly link for the whole thing. So I'm putting in the corner little links to the research papers I've linked for the research people in here. But Google Scholar works too. Now, in the K-12 space, Irene Lee from Santa Fe, who's now at MIT, does a lot of work with computational thinking. And specifically, as kids are building computational artifacts, we hear a lot that we want the kids to be creative and we want them to make big open-ended projects, but they can't do that from the beginning. They need practice, right? They need some time to get there. And so she coined this use, modify, create paradigm as a structural stepped mechanism for kids to get from using a particular concept, right? Something that replicates what we've done in the notes, making changes and either assessing predictions on that change or thinking about how the change impacts the whole, and then bringing in that higher order synthesis, creative thinking, making something larger as a developmental progression for kids through all these concepts we're working with. And so if you kind of combine those two ideas of use, modify, create, and that higher order thinking scaffold for assessment, you get to differentiate assessment using these multiple exit points. And what I'm going to do is, I've been talking at you for longer than I normally like to, but hang in there with me for a little bit. I'm going to take you through an example, and I'm going to ask you to work with the people at your table for you guys to, either in pairs or as a whole table, take an assignment that you might do in your class and apply this paradigm to it. What would be the 3 levels of the assignment you would create and give to students? All right, so after going through this, and so ask questions if you don't understand how the pieces separate from each other as we go through this example. So, the unit goal, this is a unit in Scratch for 9th grade at the Academy for Software Engineering. Credit for this assignment goes to Sean, who's the leader of the Pedagogy Meetups and who I worked with as the school was opening. And the idea is for students to use dialogue and pacing to have characters communicate with each other. The title of this unit is Go with the Flow, and it's all about students understanding that code runs in sequence from start to end. Right? And believe it or not, that's actually a foreign concept to kids. They tend to think about things in parallel. And so there's been a lot of research in this idea of sequencing of steps and statements as a fundamental concept, not only for introductory computer science, but for higher computer science, regardless of where they go. Right? In fact, back in the 90s, there was a paper that people wrote that showed that students who could take a series of steps with variable assignments like x equals 4, y equals 9, x plus y equals 7, blah, 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 blah. The kids who could do that assessment with regular fidelity, like with high performance, were most likely to not only persist through their introductory classes, but perform well in those classes and in the classes after them. So this idea of sequencing, really important for kids. So they have to create a dialogue between two characters in a Scratch program. The whole thing has to run when the flag is clicked. So requirement 0. Make two characters talk to each other. The entire dialogue must start blah, blah, blah. I'm not going to read the bullet points. What's important is they get a worked example that starts to solve the problem for them. And this isn't even the full extent of the worked example they get. The thing that the teacher walks through in that 10-minute instructional piece is actually the answer to requirement 0. And in the way that it's shared with students, it's shared not able to be copied. They cannot literally just drag the blocks over. He doesn't actually share the whole project with them. This is a GIF. And so they actually have to recreate the worked example. And there's a lot of educational benefit to recreating something that already exists. Because if you mess up, you have to figure out how the two are different. It forces you to interact with it a piece at a time and get that practice. And guess what? For that kid that was over here, how many kids who I don't know where to start, if you said, make that, right? They have a starting point. How many people's kids come 100% of the time every single day? Yeah. So if I got a kid who's out for a week, teacher, what am I supposed to do? Make that. And it gives them a starting point and a way to be engaged with the content without you having to go and sit down with 6 kids for 5 minutes each just to get them started. Right? So it's also a way to help scaffold and control for a lot of the external factors we see that influence our kids' engagement and participation in the classroom. I am a firm believer that 98% of the kids who are off task in your classroom are not willfully off task. They're not like, I'm just gonna not do whatever the teacher says because I'm a badass. That's what they emote sometimes, but most of them, I said 98, I didn't say 100. 98% of them actually would rather pass your class, right? But they don't know what to do, and they're not sure, and they lack the self-confidence to dive in, and they really don't want to look bad in front of their peers who are outwardly emoting the teacher's whack, I don't want to do this. This gives everybody a starting place. And we've seen it work really successfully, both with our strong students, because they jump in and finish that right away, and our weaker students. They have the confidence, and it's a safe place that they know they do this, they get a passing grade. And I think there's some extra percentage points for beginning this that aren't showing up here, but literally you get a passing grade for replicating the worked example in the notes. Requirement 1 starts at 0 because computer science counts at 0. Right? Requirement 1, you now need to take that simple dialogue that was the worked example and you need to modify it. You need to add animations. They have to move or do something that adds to the story. There's nothing they can copy here, but there's an entry point, right? Try and add a move block. Play with it. Make it better. Slightly more higher order thinking because they have to integrate stuff from previous lessons about moving characters on the screen. Now here comes the doozy, right? Because that kid who was in the pink block at the beginning, the one who would have passed your final exam a week ago, they just flew through 0 and 1. Here's the doozy. Requirement 2. Look at the kinds of things that happen in Pixar movies. Go and make me a Pixar movie. Right? Open-ended, creative, add your own flavor, take it as far as you'd like it to go. Kid comes back and shows you something interesting. You're like, oh, that looks really cool, but wouldn't it be also cool if it did this? Oh, yeah. Right? And the kids who are that engaged and who would have run away from everything else are now still engaged in the same project that everyone else is doing. No one is doing a different assignment. They're all doing the same assignment. You're grading the same assignment 30 times. You don't have 6 different versions of something to grade. It all fits in the same rubric. And guess what? A kid who does requirement 2 one day might do requirement 0 the next day, requirement 1 the day after that, back to 1, up to 2. You can challenge them in their own space and comfort zone very flexibly in this way without necessarily having to preset for them what your expectations of them are. So you can set high expectations for every kid every day. Diane.
What I love about this is that every kid has the opportunity to excel in their own space.
Yeah.
So, and that's what's so powerful about what you're showing. That I think what happens so often, even for gifted kids, is that we demand acceleration for good grades. And some kids are going to stay in requirement 1 and just go deeper and deeper. Mm-hmm. And that's going to be the enriching experience for them. It's, this is true differentiation as opposed to, I know that what you want is acceleration.
And it was great. It's always great to see one kid who stays in 0 all the time, and then all of a sudden steps out of their box and takes a risk and does 1 or 2, and you can call them a rock star for the day because they've exceeded their own expectations. And Sean has seen this too. You get one kid who figures something nifty out, who may not be the kid who always does the high-end thing, and everybody else swamps to that kid to figure out the nifty thing, right? Sean, do you want to add anything about this when you were using this structure in the 9th grade?
Can you give me a little more context?
Well,
I've been only here for the last minute.
Give context. So I did this in my computer science class, and each day I would give a different part of that they had to add,
Mm-hmm.
and I would give the make this blocks in the picture in the handout. But after about 5 weeks, the handout where I said make this, I would include a mistake in it in the code, so they couldn't copy it exactly, make this,
Mm-hmm.
and get it right. They had to really think through it and find the bug, and then they could do it. And so I felt like the first couple of times the make this was correct.
Right.
And then about the 5th time, what would be 5, requirement 5 or so, there would be a bug in the make this.
Yeah, and the course and the students that you're working with, like this was our 9th grade intro, 0 entry point. This was go with the flow, so this was like what? October?
Yeah, this is very early.
Very early on, still establishing classroom culture and expectations, right? You still do tiered with the AP kids, right?
Yeah.
Yeah, but it's a very different philosophy for that entry point.
Do you want me to elaborate on that? Or
I've been talking at them for a while.
I mean, so, sorry, I don't want to rehash. I guess, yeah, all I saw is the requirement 2 of service in the second one. I guess, I think just the idea that they're all working on the same assignment, and I don't know how much Leigh Ann touched upon this, but it's depth within one concept is what you're looking for. One of the things I really struggle with self-guided curricula, where I just like do these exercises, is you'll get kids who are 15 weeks ahead in terms of like they're literally covering concepts that other kids haven't discovered. And if you have a bunch of kids who are happily being self-guided, great, but if you actually as a teacher in a room of 30 kids need to sort of maintain some semblance of agreed upon classroom instruction from time to time, that can be really difficult. So saying, what is the one concept I'm teaching, and at what depth of knowledge can someone display it, so that when you go to the next assignment, it's not relying on depth of like if you have a quick example, if you had a self-guided, self-paced tutorial where after lesson X, kid gets to loops, and you have some kid who never got to lesson X, and then you want to teach a lesson that requires it or doesn't, the kid who already knows about loops is like, no, I want to spend my time on this, and the kid who doesn't is a little bit confused. So making sure that you picked one identifiable concept and then stretching that for depth of knowledge as opposed to saying move on to completely different concepts. Would be the one point. I don't know if you touched on that.
No, I didn't, and that's actually a great point. And it gets back to what we were saying about kids self-identifying as the slower, fast kids, because that kid who's 15 weeks ahead, if you're doing a class discussion, he's going to be like, oh, the answer to this is a loop. And it helps, that really helps foster imposter syndrome. I don't belong in this class because I didn't answer that just as quickly as he did, right? Trying to get over those first few second hand raisers, jump in with the right answer kind of folks. So, this is the structure of what we kind of did. So I kind of unpacked it along the way. But what I'd like you to do is with your table for a minute, maybe more than a minute, let's do a minute on each of these. What did you notice about the progression? And I kind of talked through it, but if you wanted to unpack it a little bit, how is each stage scaffolded or supported for the student? And in what ways are the more advanced levels deeper thinking instead of just more work? Let's do 5 minutes for the 3 questions with your table. Go. So, anybody want to share out something that they saw in the example or something that they had a question about or thought was a really powerful idea? I'd like to just take a couple before I give you, or something they heard at their table that they think might be unique and worth sharing with the whole room. Yes?
Well, we were just saying that this is what you do for every project, every class, every lesson. It's not just a one-off, not just a project based, but every lesson has to have that ability to be, this is what we're doing, this is how you do it, now you do it, now do it more, now what can you do with it? That kind of progression is necessary for everything with computer science.
Yeah, absolutely. Someone else?
So, since you're pulling teeth here, we like the idea of a progression starting with something that everyone can do, but the issue of scaffolding was something that was puzzling for us because it wasn't clear what the instructor was doing along the way and how an instructor might mediate a student moving from 0 to 1 or 1 to 2.
Right. So, there's a lot of, how many people talk to students one-on-one in their classroom? They go around the room, they ask questions, right? There's a lot of one-on-one instruction that happens in a computer science classroom while the kids are working, by design. And so the scaffolds are twofold. One, it's the resources provided to them. So here they're given code exemplars, right, for 1. 2, requirement 1, they're building off of what they already have. So they have a working example that they've already completed that they have intricate knowledge of, or we hope they have knowledge of. And then requirement 2, notice there's a reference to a piece of media, something visual that they can see that may not drive exactly what they're doing, but help cue where we want them to go, right? Because I could just say, I could take out most of that and write, impress me, and still get at the same higher order thinking, but the attachment to an actual professional endeavor with a piece of media is that scaffold for getting them to think bigger at that point. And then the one-on-one instruction also is a real support for that too. Yeah?
When it comes to that one-on-one instruction, if I get like 4 or 5 kids that are asking the same questions, I stop and I'm like, okay, for anybody who's not clear on how to do this, and I'll go to the smartboard and I'll do it again. And I build it for them so that there's that visual seeing what I'm doing. And the kids that got it won't pay any attention, but the kids who don't will.
Yeah, we do a lot of small group instruction, right? And if your classroom is flexible enough where they can come to a table in the front away from their computers and then redisperse, that's one of my classrooms. I've always loved the U shape with computers around the edge and tables in the middle for them to take notes or work or whatever, so we can totally bring that ebb and flow back and forth from machines. There are benefits and trade-offs to an approach like this, right? I've been touting all the benefits. There's some level of success involved for every child. They're all working on the same project. It makes your life a little bit easier. But the students can become complacent and do just enough to pass and exit too early, right? This is the one thing we really struggle with, and is an ongoing struggle, is to get them to see themselves as completer of the higher level and not just doing enough to pass. So being careful about the way that gets messaged and the expectations that are set, passing versus doing well, which we know is a problem in New York City public schools, right? Especially if you teach at the high school. What do I have to do to pass with kids who could be doing so much better? They do just enough to get by because that's all they've ever had to do. That's a real caution thing to work with. And so the idea that the task of reproducing, I added another research paper that you can check out later about the benefit of reproducing existing work as practice and for knowledge acquisition for the cognitive scientist folks. But here it's your turn. Find a partner, or you can work with your table. You're going to take an assignment, either that you currently use, it'd be great if you use one you currently use, and think about how you might structure it inside of this framework. It's helpful to think with a partner. I'm going to come around and poke my nose in and listen, and I am going to ask some groups to share out at the end so that we can get more examples. And as you share out, I'm actually going to take notes in the slides so that we all can access the examples of this later. Thank you very much. I saw some really, really great projects, and even more than that, I think what I love about this the best is that you got a chance to do exactly what we hope our students do. Try some things out, ask for feedback, collaborate with peers, have people help you calibrate, right, your ideas, and that's something we don't always take enough time for in our practice, and one of the reasons why CSNYC believes these meetups are so crucial to the community, right? So I'd like, first of all, just to thank all of you for being super engaged for that time and really working on hard problems together. I think that was probably the best thing we could do, irregardless of what came out. I know some groups are more finished than others, and I would like to document the ones that people are comfortable sharing, so I'm going to sit down and type while you present. So is there any group that'd like to go first? Group in the back. Okay. Here we have your learning objective to start, please.
Developing a circuit through hardware.
Yeah. Great.
So level 0, yeah, it was an Arduino project. Level 0 was building a project from SIGGuide. SIGGuide is just the schematics and directions on how to build for certain Arduino projects, if you don't already know. Build a project from a SIGGuide, and we have, in parentheses, hardware. And run a code from GitHub that's going to software, the one that's running that hardware. It's already provided for them, the code to run the hardware. It might be like a project that's getting an LED to blink. Okay. You ready for level 1?
Yep.
Level 1 is now, this is going to be bulleted out a little differently based on our review of this. Hack code and hardware to meet criteria. So now what you're doing basically is you're changing up your hardware. So you got a schematic of a hardware, now let's change a little. So maybe you're moving the LED to a different pin, and now you need to hack your code so it still works with that new hardware. Or adding a light, right? So you're just advancing and changing the already provided hardware. And then we're going to do a think, pair, share just so kids are talking and getting to know what others did and we're hearing what they did. So elaborating and customizing for that level 1. And then level 2, you're adding a sensor and additional code. So you're creating a relationship between and you're expanding and you're creating. So add a sensor plus additional code, create a relationship between them.
The sensor.
Right. The sensor and the LED.
Great. Thank you.
Thank you.
Does anybody have any questions for that group about their thought process? I like that they added the think, pair, share, right? After all, the projects have a twofold purpose in our classrooms. They are practice for students. They are also assessment, right? Most of the time formative, sometimes summative. And so that think, pair, share was an excellent formative assessment moment for you to determine where the students are at, what they're doing, have they really achieved level 1, and to give a clear step. Okay, now you're going to go and do level 2, and it's a great cue to get every kid to at least try it, right? And even if they do something small, they can earn one of those points. So you don't have to be all or nothing for each level. Great. Somebody else want to share? Sure, up front.
Sure. So our group came up with a concept. So the objective is to create and manage an array. And we're using JavaScript for this one.
Great. Don't worry about me typing. I'll keep up.
That's okay. And the concept we're using is for, imagine junior high or high school kids. So we're talking about a party. So they're having a party and they want to manage a guest list for a party. So we said, you're having a party, how to manage it. So step 0 is we show them code and ask them to do 2 things. Reproduce the code, but also, and this was our little innovation, is they see the code before they reproduce it. We ask them to predict what it will do. And that was Dan's idea. It's a really nice one. So basically, show them, say, hey, what do you guys think it's going to do to our? And in our case, step 0 is create an array, add some names, add a couple of names, remove a name, and then print the contents of an array. So that's enough in step 0 to give them basically an MVP, a minimal viable product, kind of a step 1 that is satisfying. They can see something. Step 1 is the idea of looping through an array. So basically do some operations, but then count the total number of guests. And step 2, we didn't quite figure out fully, but it's something like manage effectively a 2-dimensional array or 2 arrays, but basically the idea of saying who are your guests, and also track. We will ask them to say, hey, now track people's response, and that might be to create a second array where people have responded, and being able to add or change state of a guest from attending or not attending. But we will leave that open-ended. Hey, tell us who's attending.
Questions from the room for them? I have an important question. Is level 0 and level 1 the same learning objective?
Mm-hmm.
So how is level 1 count the total number of guests, the modification of something in level 0? How is it a deeper thought on create an array, add names, remove a name, and print?
The idea of looping and stepping through it.
So I see the shift from print, right? Print is your step through. Count is adding that +1, that iteration.
Because in 0, you're not looping through it. You're basically doing an array dump.
But that's what I'm saying. You're adding a new concept.
Of looping, yes.
Right. So you've actually taken this now to a new learning domain between level 0 and level 1.
Yeah.
Right? So that's something to think about. And that might be appropriate depending on their prior experience and where they are. But if you're talking about middle school kids, the idea of iteration and counting is not easy. And so you might have them in level 0 count a specific feature, right? Count how many people are coming. Or no, count how many girls are going to be there to make sure that the party's girl-boy balanced, right? And then in level 1, you might have them count how many people like pepperoni on their pizza. Count specific different features, and so that the modification is not structural, but simply requires them to address the code they've got, look at it to identify the point where that change needs to be made, and make a small change. Because in the count, you're not actually changing, you're making a real addition to the code in a meaningful way.
Yep. So
all right.
Loop at 0 or not loop at all.
Right. So thinking about how you're setting up that structure, and we do this a lot as experts, right? Because for me, as an expert computer scientist, the difference between printing things in arrays and counting the number of things in arrays is like so minimal that I don't even think about it. But for a 7th grader, that, because you said middle school to me, that difference is huge. Right? They've never counted anything in that kind of a sequence. And when you're processing lists and you have to deal with one element at a time to produce a behavior that exists across the whole thing, it's called emergent behavior, and there's been years and years of research on how hard that is. You know, you do simulations. Emergent behavior is like the golden goose. It's hard for graduate students to do. So this is where this thinking about this, one of the reasons I love that we shared out, and thank you for being willing to be open to it, is getting over our own expert blind spots about what is the same concept versus a different one.
Can I just,
yeah, go ahead.
The other thing I found related with like career array algorithms around, essentially you have some like accumulator, right? And you're saying accumulate a certain, like I'm going to hand you back one value, that's right? So like counting like how many, right? It's one number. So like sums, like the relationship between sum and count, how are they similar, how are they different? Would be, I feel like, something aligned to a very similar structure, but gets at like what is the difference between a sum and a count? Would be a good one. Also like products, if you're doing product, right? It's always initialize some variable to a starting state, iterate over everything, and the match, keep track of it in the accumulator, and then what they're focusing on are what is the keeping track operation, what do I initialize my starting variable to be? And those sort of touch this vertical alignment.
Yeah, and for you guys for being good sports, you all get CSNYC stickers. All right, does anybody else want to share? Yes.
We have a simple one.
Okay.
The objective is to learn looping to drawing geometric shapes. And assignment 0 is to learn to draw squares. Provide the code to draw a square. The first level is to modify the code to draw other shapes, pentagons, hexagons, what have you. And then the second level 2 will be to apply the looping and the shapes to an art project. Use it in some sort of drawing that can be different shapes can be applied and make cards with it.
Great. All right. Sean has asked me to wrap up. I'm happy if during the lunch period, if people who we didn't get to want to add theirs to the slides to share with everyone, so you guys have some more examples when you try and go back and implement this, hopefully in classrooms at some point, or in your own curriculum writing. I will put the link to this document in the general doc. And basically, I want to say thank you for being super engaged with me and doing a little hard work this morning.